So far we have been talking about univariate distributions, maybe multiple. So we have talked about the covariance between two x and y. Now let's go to distributions of vectors, so multivariate distributions. In this case, x would be a random vector that has n components. So we have x element Rn, for example. Many of the quantities that we have discussed for the case of single variables have natural generalizations to these multivariate cases. Let's go through them. Let's start with the expectations. So the expected value of a random variable x, which is a vector, so the expected value of a random vector is equal to the vector of the expectations of the individual components. The generalization of the variance is the so-called covariance matrix. The covariance matrix is defined as the expectation of the product of the random vector x minus the vector of expectations times itself, so the outer product of this difference. And is denoted typically with the uppercase Greek letter sigma. As we're taking an outer product of an n-dimensional vector with itself, the resulting matrix is n times n. So it has n squared values. On the diagonal, we have the variances of the individual components. And on the off diagonals, we have the covariances of the corresponding dimensions. So the entry 2, 1 of the covariance matrix is the covariance between the second component of random vector x, so of x2, with the first component, so x1. It follows also that this matrix is symmetric, so the covariance of x1 and x2 is the same as the covariance of x2 and x1, so the matrix is symmetric. On the diagonal, we have the covariance of x1 with x1, which is equal to the variance, so everything is natural here. If we know how to compute variances and covariances of univariate variables, we can naturally write down the covariance matrix of a random vector, where each entry, sigma ij, is given by the covariance of xi and xj, the ith component of the random vector and the jth component of the random vector. Very often, when we are dealing with multivariate distributions and covariance matrices, we see the inverse of the covariance matrix. We will see that, for example, when we look at the density of the multivariate normal distribution. Now, the inverse of the covariance matrix, sigma inverse, is often called the precision matrix. So if you read somewhere in a paper the word precision matrix, this is nothing special. It's just the inverse of the covariance matrix. The covariance matrix of an n-dimensional distribution is positive semi-definite. Doesn't need to be necessarily positive definite. However, it is positive semi-definite. So it's symmetric. We already know that. That's what we said, because the covariance of xi and xj is the same as the covariance of xj and xy. And it is also positive semi-definite. So for any vector x, the squared form x transpose sigma x is equal to x transpose times the definition of the covariance, so the expectation of the outer product between the difference between the random vector, the random variable, and its expectation, outer product with itself, is equal to, well, you can move the expectation out, or x into the expectation. So x is, in this case, a constant, so it's the expectation of any chosen X transpose times this outer product here. Now, because the inner part here is an outer product of a vector with itself, so for any, where it's inside the expectations, for any x that we're averaging over, that we're taking the expectation over, for any value of the random variable, this is a vector, and we're taking the outer product with itself. So an outer product matrix is always positive semi-definite. We already know that. So if we take x times this outer product with itself, and then, if we ignore so far that we're taking an average here, we know that for every value of the random variable x, this squared form inside here will be larger or equal to 0. Another way to see this is to see that if we first multiply x with the difference vector between the random variable and its expectation, we actually get a constant, and we're basically just ending up with the square of this constant. And squares are always larger or equal to 0, no matter what the value of x or little x would be. Thus, the covariance matrix has been shown to be positive semi-definite. Similar to the empirical mean, the empirical variance, we can also estimate an empirical covariance matrix. So if we have a data sample, so n different realizations of a random variable, in this case the random variable is actually a vector. So each of those xn's is, for example, n dimensional. X is a vector of n real numbers. These are all identically and independently sampled from the distribution of the random variable x. Then we can get an estimate of the covariance matrix of this random variable x, so of its components. So the first thing that we can estimate, of course, is the estimate for e of x, which is given by this x bar, the empirical mean. Again, we can use this empirical mean to estimate the empirical covariance matrix, which is defined as 1 divided by n, the sum from n equals 1 through n, so over all of our n data points, of the outer product of the difference between the value of our vector sample and the mean of all these vectors with itself. So we're taking here essentially a difference vector, taking the outer product with itself. So that's a rank 1 matrix that is symmetric, positive, semi-definite, and we are adding up all n of these and dividing by the number of data points. And that's the so-called empirical covariance, similarly to the empirical variance that we get. Again, the diagonal entries of this empirical covariance will be estimates of the variance. They will actually be identical to the empirical variance of that dimension. And the off-diagonal entries will be estimates of the covariance of the two different components. And similarly, you could here also do bias correction. Remember, we are using already the data to estimate here this expected value x bar. So we're somehow using the data twice, which results in a slight underestimation of variances. We could correct for this bias by dividing by n minus 1, which for small sample sizes might make a difference. For large sample sizes becomes less and less relevant. Now let's recap what we have learned. We've talked about the mean, which is the average of a random variable x. And if we have a sample, so n IID samples from the distribution Px, then we can use them to estimate the expected value by computing the sample mean x bar, which is defined as the average over our n samples. So it's 1 divided by n times the sum over these little x's. The expected value is the so-called first moment of the distribution P of x. And for discrete distributions, it's defined as the sum over all the possible values that this discrete random variable x can take, the value weighted by the probability of observing this value under its probability mass function. In the continuous case, the sum becomes an integral. It's an integral over the value range of x, again of this value weighted by the probability density function of x. And the integral is taken by x, so it's the integral of x times p of x dx. We've also talked about the variance, which measures the average squared deviation of the values of the random variables from its mean. And as it's the average squared deviation from its mean, it can be estimated naturally based on the sample mean. So by computing the mean of a sample, so computing the sample mean, taking each of those points, computing the difference from the sample mean, squaring that, and averaging this over the whole data set that we have at our disposal. So if we have n data points, it's 1 divided by n times the sum of the squared differences of the data point with the mean over all these data points. We said there's also a second estimate, which is given by 1 divided by n minus 1, so it's slightly modified to account for the fact that we already used the data to compute the mean. So we plug in estimate into an estimate, which creates some downward bias of the estimate of the variance. So these estimates of the variance will be slightly too small, which only matters for small n's, of course. The variance is the so-called second centralized moment of the random variable x. It is of different units than the values of the random variable itself. However, we can compute the square root of it, which yields the standard deviation, which is again in the same units as the random variable itself. In the discrete case, the variance is defined as the expected value of the squared difference between the random variable and its expectation, which, well, this expectation is the sum over all the possible values of the random variable x of the squared differences between x, this value, and the expected value of the random variable, the square of that, weighted by the probability mass function, so the probability of observing that value. And in the continuous case, the expectation is not a sum, but an integral. It's an integral over all the values that x can take of this squared difference between this value and the expected value of x, weighted by the probability density function. Now, if we have two random variables, x and y, from Rd, so they might be multivariate, then the expectation of their sum is equal to the sum of the expectations. the expectation of the difference between x and y is equal to the difference between the expectations. So that is given by the linearity of expectation. Now if we look at the variances, it's not so easy, because only if they're uncorrelated, the variances would just be adding up. So if you look at the variance of x plus y, this is equals to the sum of the individual variances of x and y plus the covariance between x and y and the covariance of y and x, as these two are identical to each other because covariance is symmetric. This is the same as saying the variance of x plus y is equal to the variance of x plus the variance of y plus 2 times the covariance between x and y. And the variance of x minus y is equal to the variance of x plus the variance of y minus the covariance of x and y minus the covariance of yx. And again, because these covariances are equal to each other, it's the same as calling this the variance of x plus the variance of y minus 2 times the covariance between x and y. And to get from here to here uses the bilinearity of the covariance, namely the covariance of x and minus y is equals to minus the covariance of x and y, as we have proved before. In machine learning, we often see transformations of random variables. And the most common transformation is an affine one or linear one. So let's consider the random variable x, which is a random vector, so it's the element rd, that has a mean vector and a covariance matrix sigma. And if we apply an affine transformation, remember, an affine transformation is first applying a linear transformation, so multiplying a matrix to x, and then adding another vector to this linear transformation. So linear, if we add something to linear, it's affine, resulting vector y. It's a deterministic function of x, so it's a linear transformation of x, or affine transformation. It is itself a random variable, and the expectation of y is given by the expectation of, well, if you plug in the formula of y, it's the expectation over the random variable x of a times x plus b. Using linearity, we can pull out a here. And as b is constant, the expectation goes away, which means that we get a times the expected value of x, which is, as we said, equal to mu plus b. The variance of y, variance covariance matrix, is equals to the variance covariance matrix of ax plus b, so plugging in the formula for y. Now we said that constants don't appear in the covariance, so we're left with the variance covariance matrix of ax. And similarly to constants that square, constant multipliers that square the variance, if we multiply by a matrix, we actually get a times the variance covariance matrix times a transpose. So we get it again a squared form here, which is equal to a times sigma, the variance covariance matrix of x, times a transpose. So these two formulas are useful if we're dealing with random functions that are linear. Now, what is the covariance between the original x and this transformed variable y. Remember, y is given by ax plus b. Well, the covariance between x and y is equal to the expected value of the product. So it's the expected value of xy transpose minus the product of the two expectations, the outer product of these two expected values. Plugging in the formula for y again, we get the expected value of x times ax plus b transpose for the first term. And for the second term, we again plug in the formula for y, we get minus ex times e of ax plus b transpose. Now we can use the linearity of expectations to split the first expectation up in ex plus b. B is a constant, so it goes out of the expectation. And in the other case, we have ex times x transpose A transpose. A is again a constant, so we can pull it out. We get the expected value of x transpose times A transpose. Here we can plug in the expected value of x, which is mu, times the constant B transpose, which leaves us with the expected value of ax transpose times ex. So this here is equal to mu, and the expected value of ax, as we have just said, is a mu. Now the transpose of this is mu transpose A transpose. For the first part we can also plug in the formulas of the expectations. So mu times B transpose is this part here, minus mu B transpose, and then all the parts that have A in them we group together, factor out A transpose here, we get E of x transpose minus mu transpose. Now this is equal to the covariance matrix of x, which means that we are left with sigma times A transpose, and here we have mu B transpose minus u B transpose. So this part here cancels, we're left with this part only, which is equals to sigma A transpose.